Now we'll start with our next program. So our next talk is, we have an invited talk by Dr. Goutam Pal, Associate Professor, ISI Kolkata. He'll be talking about public key infrastructure transition from classical to quantum paradigm. I request Dr. K.K. Sondra Pandian, Sir Scientist D, Office of CCA, to felicitate our speaker. Dr. Goutam Pal completed his BE from IIEST Sipur, MS from Sunny Albany, USA, and PhD from ISI Kolkata, all in computer science. He was a faculty of Jadavpur University CSC department for 7 years and has been a faculty of ISI Kolkata for the last 12 years. His professional research area is classical cryptography as well as quantum computation and communication. Dr. Paul received the prestigious Alexander von Humboldt Award from Germany and the Young Scientist Award from National Academy of Sciences India, along with other accolades. Till now, Dr. Paul has supervised 6 postdocs, 16 PhD theses, 24 master's theses, and close to 100 bachelor's projects. He has also authored 2 technical textbooks and around 150 referred technical publications. So far, Dr. Paul has delivered around 200 invited technical lectures as well as more than 100 motivational speeches, including 2 TEDx talks. I request Dr. Paul to deliver the invited talk.
Inviting me here. Good afternoon, everyone. I guess I am the one standing between all of you and your lunch. So I will try to finish it as early as possible. So brief outline of the talk, classical PKI. I will go over very fast because most of you already know about it. Then problems in the classical PKI, followed by the shift to quantum, the PQC standards, then PKI using PQC. And of course, when we make the transition, it has to be hybrid because both the classical and the quantum versions have to coexist for some time, and relevant issues in PQC migration. So classical PKI, we know that it provides an infrastructure for managing encryption and authentication. So the components, as we know, there is a registration authority, there is a certificate authority, and there is a directory and repository through which the sender and the receiver interacts so that they can validate each other's certificates and send information across one another. Okay. And particularly the digital signature used in PKI operates as follows. So there are several paradigms. So there is sign then encrypt, encrypt then sign. Here it is basically hash then sign. So the idea is that because the messages can be arbitrarily long, so if you want to compute signature on a long message, that's an overkill, right? So in order to make the message length fixed, first they perform the hash and then they perform the sign so that it becomes fixed length. So that's the simple idea used behind the signing algorithm. Okay. So, and we know that the modern PQC signature schemes, they also rely heavily on hashing, right? So we'll come to PQC later. So PKI architecture, we know that it works on several trust models. Particularly, there are 3 different trust models. One is hierarchical, the other one is mesh, and the other one is bridge. So in the hierarchical model, there is a root, and under root, there are several CAs, and then under the CAs, there are users. Of course, it's shown one layer, it can go up to multiple layers, depending on the depth of the network and the coverage. Okay. So the mesh PKI, as you can see that here the CAs have peer-to-peer relationship. So there is no root. So the CAs cross-certify each other. So that's why you see the double arrows running between them. And after they cross-certify each other, the users are connected to them so that they can put their trust on them. And the bridge CA, the concept is that there are two different or multiple different PKIs, right? They can have a different protocol, different standards. The bridge CA's job is to connect between the two. So basically, if the two PKIs have their different routes, so the bridge CA will be connected to the routes. Now, coming to the main theme of the talk. So what are the problems in classical PKI? So the first thing is the complexity, because the PKI is not only the algorithms and the protocols, but it also about the policies, the roles, procedures, the associated hardware, software, implementation issues, etc. Right? And the complexity makes deployment interoperability difficult. Certificates are a weak point because they have to be issued, revoked, and checked regularly, right? And if the certificate is wrong or hacked, the whole trust also breaks. And reliance on classical algorithm is another problem, particularly with the advent of quantum algorithms that are a threat to the PKI algorithms, which are based on public key. So these are the classical algorithms and examples of classical algorithms that are broken in PKI. So for example, in 1999, RSA 155, there's the 512-bit number was factored, and that broke this RSA 512 algorithm, which was used in certificate encryption and signatures. And I don't want to read them out. You can see that it comes as recent as 2020, where in WebPKI, the SHA-1 algorithm was broken by a practical chosen prefix collision attack. So this shows that classical PKIs need to be replaced, right? Because they are not secure. And you see that these attacks that we are describing here, these attacks are not necessarily quantum algorithms, right? So there are classical algorithms also, such as chosen prefix collision attack, then public collisions, flame malware, etc. Right? So there are both classical and quantum threats. Particularly in the context of quantum, we know that the Shor's algorithm breaks RSA and all allied public key algorithms like Diffie-Hellman, elliptic curve cryptography, etc. So the question is now, people may argue that we are not able to factor very large integer using quantum computer. We are doing better in classical computer, right? So the idea is that the way quantum computing is evolving, you see the IBM, they had launched 5 qubits over cloud. Then they extended to 16 qubits. And just in a couple of years, it's now 127 qubits, which are now available in the cloud. And they're projecting that in a couple of years, it will go up to 1,000 qubits, right? Whereas Google, D-Wave, and NASA, they're already operating in the 1,000 qubit range. So the projection is that in 5 to 15 years, we'll have practical, Shor's algorithm, which will be killing these PKI algorithms. So what is the current status? It's like HNDL, means harvest now, decrypt later, that store encrypted data, and so that we can break them using future quantum algorithm. So this is the time when the transition to post-quantum must happen. Okay. Apart from the algorithmic issues, the classical PKI has some system-level flaws like centralized architecture, single point of failure, because if the CA breaks, then everything breaks. And the trust has to be put on one entity, and scalability is always a challenge, right? Along with implementation error, interoperability issues, lack of cryptographic agility. This crypto agility is a term which I keep hearing nowadays in many conferences, which was not there like 10 years back. So because we have so many different systems, there are resource constrained systems, there are IoT systems, there are legacy systems. So each has its own protocols and standards and interoperability issues. So the thing is that if you change the crypto systems that are existing, how can a system adapt to it fast? That is the crypto agility. And this agility is not constant. So the same algorithm, if it is implemented in different systems, so the agility changes depending on the behavior of the system. So now shifting to quantum means the attacker is quantum, but our algorithms will remain classical. So that is the idea of post-quantum cryptography. Mathematically speaking, these are based on certain hard problem. So for example, in the lattice-based domain, one hard problem is finding a nearest neighbor, nearest vector. So you given a vector in the lattice, you find the closest vector. That is the hard problem. So in hash, one hard problem is to find collision. So given a message, you find another message which will collide with it after the hashing. So in code-based, we know that decoding random linear code in noisy environment is NP hard. So that gives the hardness. Then in the multivariate domain also, it's NP complete. So the MQ problem, multivariate polynomial, how to find the solution of those variables, right? So here is a summary of problems that define the hardness. Then the example crypto systems that use these hard problems to build reliable crypto systems. And what is the current hardness status of this? So this table summarizes that. Okay, so so in the PQC migration, there are some issues that we have to keep in mind. So one issue is that it's not a simple swap. That means you cannot just replace the existing classical algorithm and just plug the new PQC solution. Crypto agility is an issue, of course. PKI modernization is an issue because this X.509 still remains the ITU standard in all the systems. So for hybrid schemes, how do you maintain the composite keys and composite certificates, right? So that is a challenge. So therefore, the implementation has to happen in phases. Implementation wise, the size of the key, the size of the signature is also a problem, as we'll see in the next couple of slides, that compared to classical algorithms, these PQC algorithms are they have actually blown up the sizes. So practical implementing them in practical network is a bottleneck. So I'll come to that part later. This is a brief overview of the PQC competition. So there were 69 submissions originally. So the competition is happening from 2016 until recently. So after 3 rounds of evaluation, finally in 2022, they were unofficially announced. But in 2024, the official draft was released. So there are 4 algorithms now, the Kyber, Dilithium, Falcon, and Sphinx. And HQC is selected in March 2025. So this is just a brief summary of the algorithms. The crystal Kyber used in KEM, the key encapsulation key exchange mechanism, and the other 3 for digital signatures. Now this is an interesting slide which shows the growth in the key size and the signature size. So if you look at the middle columns where we have the ciphertext or output size in bits, right? And the public key size in bits and private key size in bits. So you see that all these algorithms that have been recently standardized by NIST, they work in the 1,000 range. For example, you see Sphinx Plus, it's 64,000 to 240,000. That's the output size, right? You look at Falcon, the private key size is 14,000 to 20,000. So that's an enormous size that we have to take care in order to ensure the security. Okay, so these are about the security levels. So you see that NIST algorithms, where do they stand in terms of the equivalent symmetric key? So this 2 to the power 192 to the power 256, these are the security levels, means the exhaustive search work that you have to do in order to break them. So what are the challenges when we do the migration, right? So one thing definitely is the larger key, larger ciphertext and signature that I already mentioned. But also updating the old system and library is also difficult because they are not standalone. They are interfacing with other systems, right, which are using them as tools. Okay. So backward compatibility is also an issue. As I was mentioning, that next 5 to 15 years, we have to have both the classical as well as the PQC based PKI in order to have the smooth transition. So one example I can give, let's say the root CA, right? The root certificate is valid for 20 years. So the existing certificates cannot be revoked just immediately. The systems are not going to transit to quantum. So this hybrid nature is often difficult because there are possibility of side channel attack. There are possibility of fault attack also. In fact, the NIST PQC standards, if you see the document, so they have given arguments and results, ethical hacking and ethical cryptanalysis kind of results that have talked about, let's say, the ciphertext only attack or chosen plain text attack or chosen ciphertext attack under these kind of model. But security against fault attack, security against side channel attack is yet to be explored for the PQC algorithm. So we cannot trust them fully yet. So that is another issue. And even after the migration happens, there are some issues we have to keep in mind because the standardization is still evolving. So NIST has not yet frozen because this HQC has started recently. That is one thing. Another point that is not explicitly mentioned here is lightweight devices. Okay. So we see that NIST has also launched a lightweight crypto competition, and in 2025 they have released the standard called ASCON. So they have 10 different algorithms under the ASCON class suitable for lightweight encryption, means which are resource constrained devices like, let's say, drone or sensors or RFID tags which have limited computational resource and limited memory. So there you cannot have arbitrarily large key, arbitrarily large ciphertext and signatures, right? So that's an overkill. So for that, these standards cannot be immediately applied. So that is another issue. So once we migrate to PQC, what do we do with these lightweight systems? Because these lightweight systems and IoT systems, they don't stand on their own. They have to interact with the servers and the clients and the satellites and the legacy systems. So that becomes a threat. In the classical, purely classical domain, when PQC was not existing, this problem was not there because the sizes were not that large. So that bottleneck was not there. All right. So in short, performance overhead, integration complexity, and also the limited tools and library support for hybrid certificates, that's also an issue. And of course, cost of deployment maintenance, these are always there. So I have already mentioned about agility and migration, so I will skip that part. Then constrained environment, I have already mentioned. These have been mentioned. Side channel attack, already mentioned. Fault attack, etc. So yeah, so the goal is that we have to have phased adoption, right? Hybrid scheme, pilot testing, and policies also need to be changed because we have talked so much about policies and security policies, etc. So for PQC migration, that is yet to be formed. So just to give you another update before I finish. So recently, our Ministry of Telecommunication has created a committee to look after these migration issues, like how to standardize the migration steps and how to evaluate if someone claims that, if some organization claims that, okay, I have migrated my existing system to PQC. So how to validate that, right? So what are the checkpoints that we should look at it? So in order to formulate these evaluations, we have a committee set up by this Ministry of Communications, which will work closely at the country level and also with ITU. And I'm also part of that committee. So the dialogues have just started. And we are in the process of making policy documents and drafts, which in due course of time will give more clarity and more, I would say, tools in order to implement PQC migration. Okay, so with that, I will end my talk and take any questions that you may have.
Sir, hello. Sir, I have questions regarding the applications of post-quantum cryptography. So, as when we see the standardized process of the NIST, we can only see the key exchange and digital signing. Like, is there any other applications like zero knowledge proofs and homomorphic encryption, like when the data in process? So, is it wise to actually use the post-quantum crypto to encrypt large data such as images?
Okay. Yes, so you see that in principle, if we have the key exchange and the signature, then we actually solve everything. Why? Because after the key exchange, you can switch to symmetric key paradigm, right? So you have the combination of public, symmetric, sign and hash. Everything is available. Now, why the symmetric key paradigm is quantum safe? Because so far there is no algorithm like Shor that is a threat to the symmetric key paradigm. Whether it's a block cipher, AES, or it's a stream cipher, which is Bluetooth encryption, or any other network protocol, the internet browser like Chacha or Salsa, this kind of stream cipher. Because it turns out that Grover search is the only attack that you can perform in the quantum domain for symmetric key algorithm. So if you have a 256-bit key, the security reduces to 128-bit key, not below, and you can prove that that is the optimal. So you cannot perform a better attack in any quantum algorithm. You can theoretically prove that. So symmetric keys are still surviving because of that, and the key exchange mechanism through PQC followed by a symmetric key is the current lookout for the migration. But what you are saying is a system fully using only PQC, right, without any classical, whether it's block, stream, or public, that is not yet standardized or thought of.
Sir, and I want to know about the difference between the quantum cryptography versus the post-quantum cryptography.
Okay. Yes, I see. Yeah.
Whether this quantum key distribution, whether it comes under quantum cryptography.
Okay. So when the Shor's algorithm came out, right, which killed basically all de facto public key standards for key exchange, then we knew that the symmetric key is secure, so the need for key exchange mechanism came. Now for that, one option is quantum cryptography, the quantum key distribution. So in quantum key distribution, the process is quantum. That means we are sending photons or electrons from the sender to receiver, either through free space or through fiber optic channel or through superconducting channel. But the goal is to finally establish a classical secret bit stream that will serve as the classical secret key for future symmetric key communication. So that's the QKD part. But QKD is not the only aspect of quantum cryptography. That's a major part of quantum cryptography. Slowly we are having quantum secret sharing, quantum zero knowledge, quantum secure direct communication, etc. Those layers are also coming up and adding to QKD. But in all the quantum crypto system, we have the device at the sender as quantum, the device at the receiver is also quantum, and the process in between the channel is also quantum. But when we talk about post-quantum cryptography, there is no quantum in it. It's purely classical. So the encryption, decryption, and the communication channel is purely classical. But the assumption is that the attacker may be fully quantum. So the attacker may have access to supercomputers, quantum computers, quantum memory, all sorts of quantum devices. But the user has pure old school classical machines to encrypt, decrypt and communicate. But still we can guarantee security. So that's the goal of post-quantum cryptography.
One last question. So it's regarding the source of randomness that is used in a crypto application. For example, when I try to implement generate random numbers, like I typically do using by importing functions. For example, in Python, import random. So whether it is truly random or how actually we can generate randomness in real applications.
Okay, yeah, this question is not related to the talk, but I'll try to answer briefly. So the typical library functions that provide random numbers, whether it's Python or Java or C++, does not matter. Those are very good for local randomness. Means you want to perform, let's say, some sampling. You have some data. You want to partition into, let's say, training set, test set, or you want to perform bagging, boosting, or in statistics, you want to create random samples from a set. For these kind of local applications, these random number generators are very much useful. But for cryptographic applications, it turns out that none of the programming languages are equipped to have suitable randomness. So if you have sufficiently long output, you can break it. It has been shown. Because they work on mainly congruential random number generator, like polynomial congruence or quadratic congruence, which are easily broken. On the other hand, if we want to use random numbers in cryptography, whether it's a secret key or whether it's an OTP, one-time password, it has to be perfectly uniform, no bias, no distinguishing attack, etc. So for that, we need what is called cryptographically secure random number generator, right? Which is much more involved than this library function. So typically, these are done using stream ciphers.
Sir, in last class,
yes,
in the application of quantum cryptography, so is there a quantum random number generator which can be used as an application of?
In the application of quantum cryptography, you can use both classical random number generators and quantum random number generators, right? So because it turns out that if a classical pseudo random number generator is good enough, then mathematically, as a black box testing, without looking at the inside of the device, just from the output, you cannot differentiate between a PRNG and a QRNG. Okay?
Thank you, Dr. Paul. Now I request Dr. Vishal Rathod from CDAC Bangalore to present a memento to Dr. Paul.